Okay. Hi, everyone. My name is Solvay, and today for the HICE talk, I'll be giving just an overview of methods of commissioning alignment for space-based telescopes. So, as I had mentioned, this talk is going to be more of like a previous works review, almost like a journal talk or journal club talk, and just more talking about what's been done previously and ties into the work I'm currently doing and current and future goals of that work. So I'm going to get the outline of the talk is why do we care about this alignment so much? Basically dialing in on the validity and the simulation of the alignment, what Hubble did for its commissioning alignment, what James Webb did for its commissioning alignment, and what our current plans of alignment are for a monolithic 6.5 meter 3-mirror anastigmat space telescope. And then I'm going to just briefly talk about other works in developing active alignment algorithms and what other groups around the world are doing for like simulation of very similar situations that we're doing. And then just an all in all conclusions and future work to kind of tie everything up. So first of all is a why. So if you think about deploying a space telescope, there's a lot of unknowns and uncertainties and complications that go into it. From aligning an optical system on ground, it's a lot different from on ground to in space. And there's a big journey the telescope will take, especially when we think about James Webb traveling all the way out to L2 and the fact that it was all folded up before fully deployed. You're basically just getting rid of any sort of on-ground alignment you had done. So there's a lot of factors that come into play to misalign a telescope. It could be launch, deployment, actually releasing all the optical components, as well as like space debris, like micrometeorites and things like that, and just all in all external environments in space. So this is where the importance of the commissioning alignment actually comes into play and being able to develop an algorithm that'll take your telescope from some uncertain position in orbit to being fully aligned and able to capture diffraction limited images. And right here, I just have on the right, I really like this diagram of James Webb's journey to L2 from Earth and all the different processes that go from basically being on like a folded up spacecraft in a rocket to being a fully working space telescope. And so there's a lot of components that go into play to make it work. So first, I'm going to talk about Hubble's alignment. Hubble is a Ritchie-Chrétien telescope with about a 2 meter in diameter primary mirror. And it's a fairly simple telescope when we think about its design and that there's a primary and a secondary mirror. And the main misalignment that you need to worry about when thinking about a telescope like this is just making sure that your secondary and primary are relatively aligned to one another in relation to the optical axis. And so if there's any sort of deviation from this ideal alignment, then the optical performance will degrade. And so the Hubble took a little bit smaller of a journey compared to James Webb in that it's just orbiting around Earth's upper atmosphere, but there's still a lot of uncertainties with that, and it's important to understand the optical problems that are related to this telescope when it launches. And so on the right here is just the famous like Hubble's deep field image. And this is something that probably wouldn't be able to be captured if it weren't for this first order alignment that was an algorithm that was worked on by this paper, The Control and Alignment of the Hubble Space Telescope by Gray. And in that paper, they outline just the alignment of Hubble kind of being it's like relatively simple to the optical problems that we face with the James Webb or even like Pearl. Because with this alignment, what they were doing is they were creating like a geometric model to be able to link the actuator positions of the secondary and primary mirror and be able to determine those positionings accurately. And there were a few goals they wanted to meet with these tests of Hubble, one of them being that their model was accurate, as well as they wanted to make sure that the hysteresis of the actuators didn't didn't cause any additional problems to the alignment. And with those tests, they were able to prove that hysteresis wasn't that big of an issue, which was good, and that their model was fairly valid to the on-ground situation. And when they launched up into orbit, it was the same situation. So they were able to control it from on ground and able to validate that their models were working properly and that their calculations were good. This is a diagram from this paper. This paper was released in the late 80s, and I just kind of like the simplicity of this diagram showing the misalignment of the telescope, it being kind of such a simple problem, but also there's a lot of factors that go into making sure that, that you can align this properly. So making sure that your actuators are staying within your range of motion and that your optical performance isn't degrading from any sort of mechanical uncertainties. So I just like, you think about a lot of diagrams, like I've been doing a lot of reading recently of a lot of academic papers, and it's the diagrams get more and more complicated as you dive into it. And I just kind of like the simplicity of this one just being aligned versus misaligned. But again, this is the Hubble optical design is a lot simpler compared to the James Webb, but it's also still a very powerful observing tool that we use to this day, and was able to capture amazing images like the deep fields. So now, it's all good. But moving on to the James Webb Space Telescope alignment. So compared to Hubble, there's a lot more degrees of freedom and a lot more optical issues or like optical challenges to overcome with this alignment. When developing the algorithm, there's a lot of features that need to be considered. And that was, they wanted to make sure that they can do this alignment based off of their imaging or like active capture of images. They need to make sure, similar to Hubble, that their range of actuators are managed and within that allotted movement that they can do. And then they want to be able to gather enough sufficient wavefront data to remove any sort of ambiguities between when you're thinking about like the segment and mirror, this primary and secondary misalignment, things like that. And then they want to make sure that all of this is accomplished remotely via ground operations. And so something I forgot to mention with Hubble is that with the alignment that they were performing, they had actually glued like additional optical elements around the primary and secondary mirror to be able to get more optical precision in measuring the relative alignment between the primary and secondary. So that required additional hardware on the telescope. And with James Webb, since it's a 3-mirror anastigmat design, when considering the like back-end optical assembly for the telescope, the only powered optic in that assembly is the tertiary mirror. And so what James Webb wanted to do was make sure that their primary and their secondary mirror were aligned to that tertiary mirror. So that's what it's not just a simple 2-body problem as it was with Hubble anymore. Now we're more considering a 3-body problem, but just making sure that the primary and secondary aligned to that 3rd body. So here's from this paper, there's a diagram of the actuator control and the hexapod behind each of the primary segments. So the similar control goes for the primary and the secondary mirror for James Webb, or like the primary segments and the secondary mirror. The secondary mirror was primarily used to correct focus and misalignment of the telescope. So each of the individual segments had 6 degrees of freedom to be able to that were able to be aligned, and then the secondary mirror also had 6 degrees of freedom that could be aligned. So there's a lot of interesting challenges with this. And then here's just a flow chart of the commissioning alignment. So going from the first order, like secondary mirror focus sweep, trying to find position of a best focus, and then second segment identification and fine phasing all the way to the instrument alignment. So the goal of both commissioning alignments, the front end alignment, is just to make sure that we can get to a point that we're getting starlight onto our instruments to be able to then perform instrument calibration. And so it's very crucial that each of these steps are I'm trying to think of the word. They're deployed accurate. Well, with success. It's imperative that each of these steps are done correctly. And it's important to really consider the validity of the alignment from your models and your simulations down to actually doing it in space. Because what's a little different between James Webb and Hubble, I mean, with Hubble, you were able to send missions up to fix optical problems like they had done with the primary mirror. But with James Webb, it's a little bit more, there's more risk involved because you're sending it all the way out to L2. So you can't necessarily go out to the telescope and you can't go out to the telescope and do something manually to fix its alignment. You have to make sure that it's good to go by the time it launches to the time it makes it to L2. And they worked. So this is an article saying that I think the Webb commissioning alignment took 3 months from deployment. If someone has a more accurate number, let me know. But from there, they were able to capture these images, and I believe that they did the commissioning with NIRCam, and it required a little bit more calibration on their end to make sure that the instrument was ready for this alignment. But it proved that it was successful and that they were able to actually calibrate the instrument to continue capturing the images you see today from James Webb.
So it was primarily NIRCam, but we did a lot of multi-instrument, multi-field stuff. And with Pearl and Lazuli, because we have cameras surrounding all the other instruments, we can make sure that we've got the whole field using just the context camera. We don't have to rely on doing like an IFS. Although we'll want to make sure that they're like confocal.
Definitely. And I think that like a lot of like the buildup is that with these alignments, it's like there is additional hardware this commissioning alignment is dependent on. And a lot of this additional hardware, what it can do is it can like bog down your payload and your telescope, and it just makes the overall cost of the mission increase. So what we're trying to do with Pearl and Lazuli is make sure that we can do it with less hardware and to be able to use, like the context camera to get the full field and get a better accurate alignment. So moving on to our idea for commissioning for Lazuli and Pearl. So like I mentioned, we want to be able to do it with limited hardware on our payload to try to, again, like I said, decrease the size of the weight of the payload and also just make it a less complicated process all in all. So the first step of commissioning will be once the telescope has reached its position in orbit and it's just in some random orientation, we want to start with a blind scanning approach to be able to get the maximum amount of starlight possible on our detector, and that'll be using our whatever star field is around us. After this step, we're going to go into a model-based approach to get the best possible position, just simply moving the secondary mirror in the 3 translational degrees of freedom. And if our M2 exceeds this range of motion in these degrees of freedom, then we're going to engage the primary mirror to be able to balance out that range of motion and kind of dynamically align it in that way. But at this stage, we're still just expecting the same optical performance between by moving the primary and the secondary mirror. And then we're going to go into a stochastic parallel gradient descent as for SPGD algorithm to clean up any further misalignments in M2 in translation, but also rotation. And with this method of using SPGD we're just simply like, our goal is to mainly move the secondary mirror at this stage. Moving the primary mirror will be basically to make sure that we can alleviate some of that stress of the range of motion on M2 to give it a little bit more freedom during SPGD. But again, we're primarily moving the secondary mirror in relation to the primary mirror. And like James Webb, our goal is to align the primary and secondary mirror to our tertiary mirror. We aren't worrying about the back end quite yet, but that'll be something that we worry about in future works with developing this commissioning plan. And this is where we're at right now with the commissioning. I think so far I've gotten to the point where we can go down to SPGD. I've been able to go from not blind scanning quite yet, Hayden Kim is currently working on the blind scanning algorithm, but the goal is to be able to connect all three of these to blind scanning. And then the all in all goal is to then connect all of this to phase retrieval, which Kevin is working on, and do a finer alignment. So the SPGD algorithm, we have proved that it has been able to converge down to near diffraction limited performance for then phase retrieval to take on finer alignment. But we want to be able to test these results, or the results from this, or not the result, but we want to be able to test this commissioning alignment against a Monte Carlo simulation that gives us all possible misalignment cases of Pearl and Lazuli, and just test its robustness and say, okay, it's good to go. So this is some other works in TMA alignment that are being done in simulation. The first one being the alignment of the three-mirror anastigmat using nodal aberration theory. And what this paper goes over is just addressing the concern that a lot of the computer simulated algorithms that are being developed today for this alignment don't take into account aberration theory. So they do that, or they try to do that using higher order nodal aberration theory correction. And from what I got from this paper, the main limitation that they got was that as you increase to the higher orders of nodal aberration theory, that it starts to take more iterations to perform this alignment and a little bit more computer usage. But I think this is something that I need to look more into as we consider like field dependent aberrations and maybe doing a smarter alignment for the telescope at different field points. And then also alignment of an active secondary mirror using model-based wavefront sensorless adaptive optics. Again, something we're trying to do is not have dedicated hardware for the specific alignment, but use what we're given. And with this paper, what they had done is they had basically done the alignment based off of what aberrations they could correct with the secondary only. So they were limited in that I think they could do translational like -1 to 1 millimeter misalignment on their secondary. And so they were limited in just being able to correct for that, but we're trying to go for a larger range of misalignment given what we can do from blind scanning. And so these are two papers that I'm still working on reading through and just trying to get more insight into how we can make our process a little bit more smarter, especially as we consider things like field dependent aberrations, because right now our main metric is assessing our spot size as averaged over our field. So that's what we're mainly focusing on in our alignment and making sure that we can converge it down to the smallest point it can be on our detector. But there are other things we need to address. So these are other works that I'm looking into as well. And just conclusions and future work. So for James Webb and Hubble, it was imperative that these alignment methods were tested and validated. And it just shows how powerful this alignment is for for assessing the optical performance of the telescope and making sure that the telescope is properly aligned for scientific instrument calibration. Because if it weren't for this initial alignment, it's very hard to get diffraction limited performance in images if they aren't aligned properly first. So, and like I mentioned, developing the alignment procedure for Pearl and Lazuli is underway, but there's still more to consider. And like I mentioned, all possible misalignment scenarios for given some sort of Monte Carlo simulation after the blind scanning is done, and then also be able to adapt the alignment, make some sort of smart adaptation to the alignment to correct for field dependent aberrations, and just maybe further optimization, making that algorithm run faster, because right now it does take a bit to get through all the 3 steps, but yeah. And all of this work is contributing to my SPIE optics and photonics talk in 2025. So hopefully I'll have more results then. And yeah, thanks for listening. Yeah.
So how was the alignment and commissioning procedure tested for JWST before launch? That's the part that I'm still confused on.
I mean,
Sorry. Go
No,
ahead.
please go ahead. I know, like, I was able to read the paper about like the flow chart of the process and understand the process, but how it was actually tested, yeah, I wasn't able to get that.
So I think there were two things. One is they had tons of simulations that they ran through, but the other was they actually had like ball built miniature telescope with all the segments and everything. And so they were able to do a lot of the steps.
Oh, okay. I was
on,
like, how do you get a star for JWST on the ground? So
don't-
if they have a miniature telescope, that makes more sense.
Yeah, I don't know exactly what their core simulator was like, but yeah, they had a, you know, I don't remember what they called it, right? But they had a miniature JWST.
And it was just like tiny hexagonal segments that they.
Yeah, I don't think they
and-
were that tiny, but I think it was pretty substantial.
Oh, okay.
But yeah. But then yeah, they had very thorough simulations where they would like point at star fields and simulate that and go through all of the commissioning steps using, you know, flight software just with simulated inputs.
And I think that's what Hyungmo is currently working on right now, is building like a mini telescope simulator for
He is, and he just got his OAPs, you know, a week or so ago.
Perfect.
So are you able to work with that and test out any of your?
I want to. I told Hyungmo I'm interested in helping build it, and also I think one of the main things we're going to do is test like SPGD on the telescope simulator.
Okay, so deliberately put in misalignments, make measurements to
Correct.
get
Yes.
whether your software tells you
Yes.
the right direction and magnitude to fix it.
Mm-hmm.
Cool.
So can I ask, these algorithms, do they have to run on board, or can you run them like on the ground and like transmit what the telescope has to do?
For Hubble, I know for Hubble and James Webb, they both did them on ground.
Okay.
It was on ground and transmit. I'm not sure for Pearl and Lazuli if we're expecting to do like autonomous. No, okay.
I'm
I
just,
mean, like,
I don't think we can.
not fully autonomous, no. I mean, if there's parts that, I can imagine like once you have the star on the detector and then like the SPGD part, maybe that's something you might be able to think about automating, but like the early stuff, I think we'll just be staring. We'll stare at a place where we'll be stable and yeah, take our time.
The mechanical structure of the telescope are considering in those calculations, or you just assume that you made the best that you can do and consider the environment changes, and or in other terms, it could be assessed if there is some changing of the structure of the telescope, or
There's some that needs to be considered when we're doing this alignment. So right now, it's like with the commissioning that we're at right now, it's done. It's not connected to the like context camera right now. Cause like I think that would be the full loop, is assessing like how it changes over time and like getting our exposure time down and like taking noise into account. But also that's also a question of like doing it on ground, like assessing how the mechanical structure changes from ground and then seeing how the
so
algorithm
there's some of
adapts.
that's expected, like if you look at the motion budgets of specifically the hexapod and M1, there's numbers there that account for things like a one-time shift of your structure or gravitational release of optics and stuff like that. So there's terms there for that. So those are the types of things that have gone into this in terms of when they start with their starting positions, how far away do they start? But as Solvay was saying, there's not yet the realism of you may have thermal changes that are happening while you're actually doing this alignment that are happening underneath you. And that's something we certainly still have to do.
thermal control would play a very important part on this, right?
Yeah, exactly. Yeah. So I mean, if you take, this is why we talk about this in our kind of ConOps discussions about how we would stare for a long time at one place in the sky to basically become as close to thermal equilibrium as we can. So like if we were to like slew and change the spacecraft orientation and then try to align, I think it'd be brutally hard, because the system would be changing underneath us basically too quickly. So for like the initial alignment, we're gonna have to go to a place that's fairly stable and go from there.
If I could add something on this, is it possible just by the optical measurements, you detect that there is some out of loop change of temperature, or?
So yes and no. You will. Wait a second. I'm gonna let Solvay try and answer this first.
Oh, no. Yes and no. I think like, because right now we're assessing spot size, right? And that is it's not a very informative metric. Like it tells us just the all in all just performance of what's happening on the detector. But like changing thermally, I don't think we can really, like, we can't get fine enough precision on what's changing thermally without like a wavefront or an OPD.
Yeah, so another way to say that.
Sorry, on that point, you said you're evaluating spot size, and I have been wondering, like, what is the metric for SPGD?
It's the average spot size across the detector, or like RMS spot size.
But when you're getting like real images, is the spot size, are you just gonna do like PSF size then?
Yeah,
Make that the metric?
essentially, yeah. Mhm.
PSF is.
And then, yeah, you're gonna have to do some thresholding or something, because the PSFs are gonna look weird. They're gonna be streaks too.
Yeah, and it's like right now it's like the metric is being measured in Zmax, like it's a Zmax calculation, and it's when you look at there's not really a lot of thresholds put in place right now that like make it look a certain shape. You know, like measuring the ellipticity is something that should go into the algorithm as well, but right now it's just that's not being measured.
So kind of to answer your question a little bit more, so Solvay said basically that you only get one number, maybe two numbers from your focal point wavefront sensor, right? You see a shift or a deformation, but it doesn't tell you what moved in your system. So you don't know if did M1 shift or did M2 shift. So you can't, you see something is wrong, you see something's changed, but it doesn't necessarily tell you what it is offhand. Like we would have temperature sensors and stuff where we can measure, you know, the temperature of the secondary or the truss or whatever we think, you know, we'll put them where we think it tells us where something is moving. So there will be information to help us whether or not things are stable there, but you don't just get it from the wavefront sensor.
It almost argues for some autonomous corrections, because if all the corrections come from the ground, the amount of change you can get between measurements might be too big and you never close.
So I think that's gonna be the trick, right? Is like when you have really large errors, like the misalignments are gonna be far more significant than what like a thermal creep would be, right? But eventually, as it gets tighter and tighter and tighter, that's when you have to shift into your continuous wavefront sensing, right? And we have to run a simulation to see where that kind of when that starts to matter. Like, does the thermal creep start dominating below 2 lambda over D when, not 2 lambda over D, sorry, below 2 lambda or 2 waves when the continuous wavefront sensing starts kicking in? Or does it happen before that, in which case that'll complicate our lives, because that means the SPGD is basically having the ground truth changing out from underneath it. So that's on the future work category. I think the answer is we can probably get the 2 lambda without having to worry too much. In the case where we're staring in one place for a long time and it's fairly stable. I do worry about when we do a big slew, we get a large thermal change. That's the scary one. Yeah.
You're going to find all your sources like in the images. You don't have to know a priori where everything is going to be, etc.
Am I? Or
Yeah.
maybe. I don't know. I don't know necessarily from. I think the goal is to just use everything from imaging to drive the alignment. So
It's going to feed into how often we have to calibrate pointing and improve our
Yes.
pointing knowledge,
yes.
which will start out terrible.
Yeah. Yeah.
And then steadily improve, but you know, every time we make corrections, they're going to change it.
Mm-hmm.
Yeah.
That's another factor to play in is the looping and the pointing correction into all of this as well. Because right now it's like if I'm starting at some terribly misaligned scenario, it's like I'm manually changing like the field bias in ZMAX, which is like my equivalent of changing the pointing, but that's not necessarily what we're going to actually be doing. So it all needs to feed into each other at some point. And I think there's still a lot of questions that need to be answered with this work. But yeah.
How often do we think like we're gonna break the loop so that we have to just run phase retrieval? Is it like when we slew? Is it every time we point to a new field? Is it? Because my understanding is like supposed to be continuous. So let's say it breaks the slew, but it shouldn't.
You have to ask someone who runs an intent model, which is what your error is a function of time.
What?
What?
I'm just like how from what you said, like in thermal things break the closed loop while you're still on a field, or is that?
I hope it doesn't happen while we're still on.
Yeah, it should have.
Although
you're sitting there and staring unless something.
but we are like doing measurements every 60 seconds. If the focus is changing, say the secondary mirror support struts are changing in length, because we're not keeping them steady in temperature, you could end up having fairly significant focus changes. So we're prepared to use temperature telemetry. Well, prepared. We know that we probably need to use temperature telemetry to make two focus corrections, maybe on a 10-second cadence, rather than just waiting on the 60 seconds phase retrieval.
Okay.
But that's complicated because then like during a 60-second measurement, Kevin's going to be making use of, if we're making focus is drifting and we're trying to correct it all.
Is it purely a correction or is it also predicting based on your telemetry?
So we would probably have to do some predictive.
Okay. That makes sense.
Okay, this is why we want to be more stop model. We have initial stop models that show that trend is pretty darn linear. So like prediction should work okay for focus, but might not work very well for other terms. And yeah, anyway, so hopefully trying to redo the stop modeling for a long time. And then, because one of the big things I'm interested in is like, yeah, when you do a slew, how much wavefront error are you starting with? Are we in the capture range of the continuous wavefront sensing, or are we outside it?
Out of curiosity, how